entropy, and of course, that's the same as summing over k of pk log of 1 over pk, of course, because 1 over log of 1 over is minus log. It's incredibly important, but it's a bit of a distraction. It really, it doesn't have anything to do with what I'm talking about there. I forgot to say the entropy. So L is Q over P. All right, so I chickened out in the notes. I said, let's just stick to discrete random variables. You're all too stupid to think about anything else. Well, you're not too stupid to think about anything else. For a discrete random variable, it's very easy to explain this. You know, you look at where these guys have mass, you take the ratio and take the log, that's it. That's the log likelihood ratio. But in general, it just means that. It just means that take the exponential both sides. It just says that Q of dx is equal to e to the L of x, p of dx, and if that bothers you, well, what I mean is, if y has distribution q and x has distribution p, then what is the expectation of y? It's just e to the L of x times the expectation of okay, I mean, so whatever it is, if it is densities, whatever it is, you're just basically taking that distribution and multiplying it by e to the L. Okay, that's what I mean by log likelihood ratio. I will stick to discrete random variables because it will make things a little bit easier, but I don't need to. You know, basically, you know, having a log likelihood ratio existing, I didn't have to say, I could have put in a g of y here. In fact, I wish I had. Slip in a little function there. You know, I didn't have to just say the mean of y, mean of any function of y, if that it makes sense, provided it's defined. So g is measurable, the expectation's meaningful. You know, it's not infinity minus infinity. So this is a likelihood ratio between the two probability measures. All right. So if you've got a likelihood ratio between the two probability measures, you could take its log, which is capital L, and you look at the mean of L with respect to Q. And that's the relative entropy. And that is the most fundamental object on the planet. It's absolutely incredible. And that's what gives you these points. It's what allows you to come up with that result, everything. And that's what we need to understand as we go along. So it's 4:40. We're supposed to break in 10 minutes? What? Any questions? Either answer a question or I just give you the AEP real fast.
So
Yeah.
This is discovered by information theorists?
Oh, no, not at all. not at all. I mean, this has been around. I mean, statisticians were playing around with relative entropy forever, but Claude Shannon put everything together. I mean, and a lot of things were invented after the fact too. So a lot of things came about. I think that the whole field of large deviations became hot only because of Claude Shannon. I'd say that. Sturck and Veradon, who are the godfathers of large deviations theory, their entire motivation was the beautiful information theory from Claude Shannon. So I think that he motivated a lot of mathematicians to work on this.
This idea of entropy wasn't.
It's been around forever. Entropy is as old as the planets. I'm just saying it's a foundation for information. I'm saying it's a foundation for information theory. That doesn't mean information theorists invented it. Yeah. Yeah, absolutely not. Although information theorists did a lot.
Here you're saying that P and Q are actually continuous.
No, that's what I'm saying. You don't need anything. They can be anything.
Oh.
Yeah. It just means that if I want to compute the function, expectation of some function of y, I can do it by taking expectation with x, but putting in this likelihood ratio.
Given that they're related.
Yeah, that's right. So, that's right. Otherwise, it's infinity. Otherwise, by definition. And this definition really makes sense, because what you could do is you could approximate Q by a probability measure for which a likelihood ratio existed, and let that approximation get finer and finer, and you'd find this would go to infinity as the approximation gets finer and finer. So if there's no likelihood ratio, if that doesn't exist, it's infinity. Yeah. It has some wonderful properties.
But it can't be negative, right?
Next lecture I'll tell you all about it. Yeah, it's convex, it's non-negative, it has all sorts of nice properties. So I'm not going to be able to finish this, but at least I can say something about it. Why this guy is so important. And you don't need IID for this. Again, it's like we just don't have time to go into everything. So, I'm saying IID, but it's not necessary. So again, let's take the IID case. But again, it could be Markov, it could be all sorts of things. And let's look at a vector. Okay, so if this was an information theory course, this would be a word in my code book, basically. Now, the distribution of this might be some crazy thing. Again, it could be a mixture of a billion Gaussians, an exponential, or throw in a few Cauchy distributions, mixtures of all of them. It could have, you know what I mean? It could have it doesn't have a density, but if you try to draw P, it would just, have masses like that, and just crazy thing. It's incredibly complex. What about this guy? What's its distribution? Given that this is so complex, oh, that's right, entropy, it's discrete. Shit, forget it, I made a mistake, you can't have any density parts. All these are just approximations of arrows, I'm sorry, arrows, delta functions. So what's the distribution of this xn? This is why entropy is so important.
The joint?
What's that?
The joint distribution? The joint distribution?
No, the whole thing, it's a big vector, it has a distribution, right? It's a random vector. But let's give it a name, let's call it Vn. So this is really complex, just has big mass, little mass, all sorts of things. It's supported on 10 trillion sample points, but it has an entropy. All right, this could be infinity. Couldn't it? This could be infinity. if you have an infinite number of samples, it could be infinity. So it turns out it's uniform. It's a uniform distribution, very, very approximately. So there's something called the the AEP. I'll write it out next time. It's uniform, uniformly distributed, equal probability of being anywhere on I took a natural log over there, on e to the n HP points. Okay, so there's basically that many typical points, and with overwhelming probability they're going to be on those typical points. It's crazy, and it's so simple to prove. If you gave me 2 more minutes, we could do it, but let's not rush it. We'll do it next time. It's a 5-minute proof. It's the law of large numbers, and you're done. Yeah. So I mean, the thing is that you see the proof, you go, oh yeah, big deal, but it's remarkable, And so this is the thing. This is why it's like a first step in an information theory course. It's how you can blindly come up with a code book. You say, I've got, say these are binary. They take on values 0 or 1. And I'd like to be able to generate a code book. Well, you can generate very distinctive, that many code words, no more, and they'll be far apart in some sense. So it's quite a cool fact. But that's really far from the course, though. It's really cool motivation for why people care about this. It's a dead end, though, in this course. Anyway, but I'll give it's a 5-minute proof. We'll do it next time. All right. We'll do that at the beginning of class really fast, and then we'll get into all the pretty geometry I mentioned. Right? And solutions to homework will be up quickly because I can use yours. I already saw some of the submissions. They're awesome.